So good morning, everybody. Good afternoon, wherever in the world you are. Welcome to this meeting. We are beaming out from Nairobi, Kenya at the Strathmore University. I've looked onto the Zoom meeting and there's loads and loads of people from multiple sites. I'm going to be your host for this meeting. My name is Colin Pillai. What I see is that we have individuals from Sweden, from Seattle, from Dublin, from Nigeria, and of course, I don't know all the places that you're dialing in from. So I'm going to ask you to tell us about that in a minute. Here's the faculty. In this presentation today, Steve Kern. Thank you, Steve, for staying awake till very late. It's very late in Seattle. Steve works at the Bill and Melinda Gates Foundation, and he's responsible for supporting and directing quantitative analyses on various global health programs. What Steve will do is he will take about 15 minutes and will lay a context for today's malaria vaccine modeling webinar. The bulk of the time would be taken up by Michael Dodds. Michael's an engineer and has actively worked on various pharmacometric and mathematical modeling projects, but in particular on modeling the RTSS vaccine data. So Mike will take up the lion's share of the time. At the end of that, we would have Aida Kawuma, and Aida is dialing in from Uppsala, Sweden. Aida is a pharmacist and a doctoral student. She's currently attending the Uppsala Pharmacometrics Summer School, and she will then provide an overview of our plans after this inaugural webinar, and more from Aida a little bit later. And in the last picture, for those of you that don't know me, I'm Colin, and I'm a clinical pharmacologist, and I'll be moderating today's session. With that, let me now hand over to Steve. Sinead, you could mute me and unmute Steve. Steve will also then present his slides directly from Seattle.
Good evening, good morning, good afternoon to everyone, wherever you are. As Colin mentioned, my name is Steve Kern. I'm Deputy Director of Quantitative Sciences at the Bill and Melinda Gates Foundation. And I lead a team of people here that are focused on supporting our partners who are developing new drugs, new vaccines, new vector control tools to help lead towards malaria elimination and eradication. So I'll give just an overview of modeling and its efforts in essentially supporting the development of new malaria vaccine candidates. And then Mike will take over and focus in particular on efforts that he's been doing working with our team. So we've made some great progress in malaria eradication since 2000, with a great decrease in incidence rates and mortality decreases, but we still have a long way to go. And here is this curve from Chris Murray's team at the Institute of Health Metrics and Evaluation, and the World Malaria Report shows the incidence rate has been declining again since 2000, 2002. And I would say just recently, actually in the most recent report that came out, we've actually shown that this curve is flattened. And so we've maybe stalled a little bit in our malaria eradication effort. So we've made good progress, but we still have a ways to go. And I'll call your attention to looking at this curve to the right that shows a histogram of where the incidence and particularly the mortality tends to lie, and it's with the youngest children, the ones who are first exposed to malaria. And so that's the area where there's still a large effort needed and ongoing for protecting young children, and a big focus of the vaccine effort, in particular with RTSS. So if we think about the malaria parasite infection cycle, we have some opportunities here in the life cycle with natural bottlenecks. And these natural bottlenecks, the number of parasites that are present either in the host as the mosquito or the host as human is narrowed. And those become the places where much of our therapeutic effort is targeted, at least in the vaccine world. So in particular, draw your attention to that red box to the right that says about 100. So that's where the sporozoites in a bite of a mosquito to a human first gets transmitted. And the vaccines that we're going to talk about today, which are called pre-erythrocytic vaccines, they tend to work in that space between the bite and the development of what's called the liver schizont. That is, when the parasite takes up in the liver and they start expanding from there. Now, malaria has some unique opportunities in terms of using models to inform development. Here, this box is from a recent publication by Kayla Andrews that talks about the efforts in drug development. But I would offer that there's very similar aspects and advantages into vaccine developments as well. In particular, the development of relevant animal models that can actually give some insight into the potential pharmacology and activity of new agents, and the controlled human malaria infection model, which is really important for being able to test the potential efficacy of new compounds, whether they're drugs or vaccines. One thing we need to keep in mind if we're talking about eliminating malaria from a population or from a region is that this is a multifaceted project and challenge. And so while often we'll focus maybe on one aspect of the elimination armamentarium, either drugs or maybe vector control, a case detection, or the vaccine, and each of those elements has multiple components that can be contributed in thinking about their impact in these areas. It's really important that we actually lump them together and think about using them together to be able to actually have an effective approach towards elimination. So whether we're in the development of a new drug or a new vaccine or a new agent in the vector control space, or thinking about how to implement reactive care to ongoing infections, we need to think about this in the continuum of all those pieces working together, because as they work together, they actually start to develop some degree of synergy to be able to get towards this goal of reducing infection in the human population. One of the ways that we explore this is through what are called epidemiological models in particular. And the epidemiological models are oftentimes agent-based, or they can be called compartment models. But the idea is that you can then simulate these multiple interventions and start to explore the factors that seem to be the most important towards getting to a state of elimination. So here you see some heat maps on the right. They're from a publication by Philip Eckhoff in the Malaria Journal in 2001 that show the impact of coverage of an intervention. In this case, it's a vector control intervention of insecticide-treated nets on the x-axis, or indoor residual spraying on the y-axis. And you can see as we increase coverage on both, then we get to this blue zone, which is actually the place where you have a high probability of malaria elimination. The red zone are places where you don't. And so it's important that we explore not only the fact that we're implementing these new interventions, but that we're doing it at a certain level of effectiveness to be able to assess whether we're going to achieve a goal of eliminating infection from a particular region in the world. Also notice that factors related to the mosquito are important as well. The bottom curves show the percentage of indoor feeding of a particular species of mosquito, and then also how much human biting versus other host bitings, animals in particular, that a mosquito takes. And so the mosquito's behavior is also an important component in this system. So we want to make sure that we have simulation models that explore these dynamics. Here's another example from the group at Imperial College in London, where they looked at different factors that might be able to reduce the incidence rate in certain populations in different geographies throughout sub-Saharan Africa. You can see each of these curves is labeled by a different community, and then the factors that are shown there are different interventions, from long-lasting insecticide nets to screen and treat with new drugs, as well as adding on indoor residual spraying and mass drug administration campaigns. But importantly, note that as we add these different components together, we get greater and greater effect, but they're still not reducing the infection rate in a region to 0. It's also important to look at the variability and understand how much variability might be present in our simulations. That gives us a sense of how much we can trust their estimates to be able to tell us the likelihood that some intervention that we're going to carry out is going to be successful or not. So here is from a paper by Aaron Stuckey, who is at Swiss Tropical Institute in 2012, that shows a number of different factors and the variability in the simulation. And this is from simulating populations of 10,000 individuals. And we get a sense of how much each of these factors is contributing to a magnitude of reduction in malaria incidence and the range of variability that happens there. So it's important to keep all of these factors in mind when we're assessing a model or using a model to assess an impact of a new intervention. And then what to do where is really critical when we think about the factors that also add to this complexity, and that includes the seasonality and vector composition and transmission intensity in different regions of the world. So here you see some heat maps, again from the group at Imperial College, that's showing the probability of reducing or eliminating malaria in different parts of sub-Saharan Africa based on the interventions that we have available or the tools we have available to us today. Those include nets, indoor residual spraying, mass drug administration, and then combinations of those. And I'll point your attention to the fact that where this classroom is actually sitting in Nairobi is one of the regions on the maps that's listed or colored in gray. And that gray indicates that basically we don't have the tools available to us today to completely eliminate malaria from those regions. And so we need further development of new tools to be able to do that effectively. So today we're going to spend time thinking and talking about vaccines and how we might be able to use some of the modeling tools that have been extremely effective in drug development and start to think about their role and their potential in vaccine development and how they might help us plan some trials. Vaccine development is a long, arduous process. This is a slide from GlaxoSmithKline, who is the maker of Mosquitex, which is RTSS, the anti-malarial vaccine that Mike Dodds will talk about later today. And you can see this has been a 30-year process that's still ongoing. They're about to start large follow-up trials in children in 3 locations in Africa, again, to move this, this vaccine forward to understand how to optimally use it in an effective way. One of the things that's been able to help the development and the assessment of the impact of these vaccines have been the use of these epidemiological models. So here is results from the Malaria Modeling Consortium team that's been involved in assessing the impact of RTSS as a vaccine and looking at the cost effectiveness of this vaccine in the populations where it's been treated. And I want to point your attention to a couple of things. Notice each of these bars, the colored bars, is a modeling result from a different group. And no group has the same result. And that's not surprising. So when we have different modeling groups using different models to simulate the same situation, they're not likely to come up with exactly the same numerical result. But importantly, the trend is the same from all the models. And so this becomes a way to essentially help use a validation or a corroboration, if you will, of the models to be able to say that they're likely to be describing the data and the situation as in a reasonable manner. And so what you see is that with increasing level of prevalence, you see a greater decrease in the number of malaria cases that occur per 10,000 patients. And this looks at both the 3-dose and the 4-dose schedule that was tried with RTSS. So one of the things that we would like to explore ultimately is what do we need in an effective malaria vaccine? And so I'll point your attention to this paper by Edward Wenger and Philip Eckhoff at the Institute for Disease Modeling, where they essentially simulated ideal characteristics of a vaccine to see what it would take to essentially get a certain region or an area to an elimination state. So what you see here are 2 examples of different levels of endemicity indicated by this variable EIR. So a high number means there's a high intensity of infection. A low number means there's a relatively lower intensity of infection. These are simulations for a single species of mosquito, so Anopheles arabiensis, and actually simulated at different levels of indoor feeding rates. And that's important because bed nets generally only work when you have mosquitoes that bite indoors, because that's when people sleep under bed nets. And so when we think about combining some of these interventions, it's important to consider all of the factors that can contribute to variability in the response and the likelihood that these interventions will work. But in this paper, they were able to begin to define the characteristics that would be needed in an ideal vaccine if it were going to have an impact that was going to be sustainable. Here, the simulations are just a single mass administration campaign, so not a repeated campaign through the population, with a 5-year life of the vaccine, or a 5-year duration, let's say. And so what you can see is that under the right conditions, in terms of effectiveness in net coverage, and also effectiveness in being able to reach the population, you can in fact drive the elimination of the parasite prevalence, in this case, down towards near zero with an effective vaccine. And so given these characteristics, then that can help us understand and define what we might be looking for in the next generation, or how do we effectively use the tools that we have today to be able to essentially move our efforts forward in developing new vaccines for malaria. So with that, I just want to highlight and point out the consortium members and people that have been involved in a significant amount of modeling and population modeling for malaria. And I want to then turn it over to Mike Dodds. And Mike is going to start to talk about, specifically with regard to RTSS and vaccine development, how we can begin to think about quantitative modeling approaches that would give us some sense of the ways that we might be able to maximally develop or identify the characteristics of a vaccine that can reduce malaria in a population. So I'll stop there and turn it back over to Colin as the moderator.
But Steve, could you make a comment about the efficacy of RTSS as a prelude to Mike's presentation?
Yeah, so I mean, it's a challenging value to assess, partly because it's changing over time in terms of the duration of efficacy. So initially, the efficacy is quite high with RTSS, in the 80% range in terms of overall effectiveness. One of the challenges you see is that efficacy drops off rather quickly. So while it is an effective vaccine, it needs to sustain itself longer if it's going to be used as an effective tool in an elimination campaign, right? So important to think about the fact of, if we're going to combine this vaccine with other interventions to try to eliminate parasites in a population in a particular region, a longer duration or longer lasting vaccine would be a desirable characteristic. So one of the challenges that's going forward now with RTSS is looking and exploring at whether there are other ways to administer it or other things to combine it so that its potential can be maximized.
So thanks, Steve. And folks, so now let me hand over to Mike. So many of the people on this webinar have been involved with RTSS. Just looking across the room here, Professor Bernard Zogutu, who's our host here at Strathmore, has been actively involved as an investigator. Some of you may have been involved as investigators or people analyzing the data, or you might even have been a subject in the study. So it's for that reason that I'm very grateful that Mike offered to do this particular webinar as our inaugural webinar. As a reminder, Mike is an engineer and has been actively involved in this type of analyses. So Mike, over to you.
I've been in Kenya now for a few weeks, and I've found the Kenyans to be uniformly very friendly and very accommodating and very welcoming, and my hosts here at Strathmore have been no exception to that. On this travel here, I was alerted to the fact that there is going to be a sort of a phase 4 study in hundreds of thousands of children in Kenya, Ghana, and Malawi. And that's going to start in October of this year. That's going to be in 5 to 17-month-old children, and the idea is that study is going to run through 2020. So having a model in hand, an idea and some predictive capacity to understand what might happen in those children, I think is a fantastic tool and should be explored. Again, a little bit about my background. As an engineer, I find it very rewarding to work in the field of medicine. And most of my background has been working with biologics, large molecules, antibodies. I should preface this conversation with the idea that pharmacometrics, or the analysis that we're talking about here, it really hasn't been much done in vaccines. So this is really fertile ground. No one has spent a lot of time doing this kind of work. I think our epidemiology colleagues are very far ahead in this area and have really been leading the charge. But I think the pharmacometrics area needs to lean in here a little bit and think about how to lend a hand in vaccine development. So the problem statement, I guess if I had to put it bluntly, if we were to develop a second-generation malaria vaccine, if we were to change something about the product qualities of the RTSS vaccine, what would we do to adjust the protection available with this new second-generation hypothetical, strictly speaking, vaccine? I mean, there's lots of other things we could be doing with this model, but I think this is an interesting thought exercise, and one which I hope is very relevant to this community. We've got available, again, from the Imperial College colleagues, a pretty simple and practical model for RTSS titer levels. So that's the antibodies that get generated in the course of vaccination, and then how those antibodies then relate to efficacy in a global setting. And that shows us, unfortunately, that the protection is below maybe 50% after 8.5 months. Not surprisingly, the Mosquitryx trial that's going to be carried out at the end of this year will have a series of 3 vaccines a month apart, and then a gap of about 18 months to revaccinate these children. So you can kind of see that revaccination after 18 months is really there to address some of that shortfall over a long period of time. And we'll look at some graphs of how that works, right? So already we can kind of see the clinical protocol is sort of thinking about how to adjust for that fact. So we can use this model, which is informed by global phase 2 and phase 3 studies, to predict titer and protection in children, adolescents, and adults. As a function of time, as Steve alluded to, that the protection sort of rapidly diminishes in the first few months. And then the product qualities, what the potency of the molecule, how long does it last, how long does the immune response last? And we can use that then to do some forward problems, some simulation, if you will. I'm going to focus on very practical tools and the critical thinking that a pharmacometrician needs to address these questions. And importantly, how we need to communicate those results effectively, right? It's a great paper by Jeff Barrett that came out in 2008 that explains what is a pharmacometrician. And essentially, it's not any one discipline. It's engineers, it's applied mathematicians, it's clinical pharmacologists, it's MDs in some cases. And so we have a very heterogeneous set of backgrounds, and we need to be careful about how we communicate our results to that heterogeneous group, as well as other stakeholders, particularly in the public health area, right? So we can't launch into an exposition of a bunch of mathematics. That's not what the stakeholders around, especially this sort of vaccination campaign, want to see. They want to see graphics of protection. So some of the discussion today is going to be, how do you present these results when you end up with lots of simulation cases in a way that's digestible to non-specialists, particularly public health officials that are making decisions around, should we vaccinate 120,000 Kenyan children? Right? That's a big decision. I'm going to use the open source system called R, and I'm going to use that to work through this problem. I'm not particularly married to that one particular tool. It's just a very common tool that's used in pharmacometrics and other disciplines, right? And you'll note from the course download materials that all of the code required to reproduce this work is available in that zip file, right? So you can look at the graphics that come out of it and use that to kind of kick the tires. And there's a couple of sort of, quote, homework problems, if you will, that's in there. Another great thing for a potential follow-up would be, well, if we can get a hold of that protocol, that's going to be run in October of this year. Why don't we use that to run some simulations around what might happen in terms of protection over time in those children? And there we might extend the simulations to account for enrollment. Not everybody's going to get dosed at the same time. Perhaps include some seasonality of infection and attack from bites and malaria. So, this is, I think, a good, I want to pose this discussion as kind of a jumping off point, right? This is a start. Also, I'm going to introduce R-Shiny as a useful framework for communicating these results to non-modelers, right? And again, that code that you need to deploy that simulation as a web-accessible application is available to participants. R-Shiny in and of itself is kind of an interesting whiz-bang, I guess, tool available. But where I find it extremely valuable is in an ambassadorial function, right? You can provide this tool to MDs, to public health officials, and then they can actually then run the model simulations at their desk using a web-enabled framework, and that allows them to kind of kick the tires, if you will. And I think that's an extremely valuable ambassadorial activity that modelers need to get better at. So let's look at some of the results from the original modeling paper. And again, this is from Michael White and others from Imperial College in Osregani. What you're looking at is a series of plots in the red curves at the upper left and the center left of the screen describes the antibody response. After the first 3 monthly injections take place, we can then measure antibodies that are specific to the immunogen present in the vaccine, right? So we can get a sense, this is concentration, how many antibodies are present in these subjects post-vaccination, right? And you can see that starts at a reasonably high level. So the upper left panel is for relatively young children, 6 to 12 weeks. And the titer value starts at around maybe 100 or 300 EUs per mil, right? So that's a concentration unit. To the right of that, you can see a very similar profile, but now at 18 months, and again, this is the protocol that's going to be carried out in these 3 African countries in the fall. About 18 months after that first series of vaccinations, they get a booster dose, right? And you can see that the antibody levels then jump back up and have this kind of biphasic decay, right? So you can appreciate there that there's an initial relatively rapid decay. Again, we're looking at the data on a logarithmic scale, and then a relatively long plateau. So that's for the 6 to 12 week old children. The actual protocol that's going to be going on later in this year is going to be in children between ages of 5 and 17 months, right? That's where the largest amount of deaths occur, at least from malaria. So that's the group that's being targeted by this intervention. They're in the blue in panels B and D. And again, you can see a similar pattern where if we revaccinate in panel D at around 18 months, we get this sort of jump back up of antibody titer. You can also appreciate that the concentration levels are relatively higher in these older subjects, right? The 5 to 17 month old subjects just have a higher titer level, right? And if the amount of antibody titer is somehow tied to protection, right? We want to have these antibodies present in circulation, so when they get a bite and circumsporozoite that enters the bloodstream, we would like that circumsporozoite to be coated with these antibodies. So there's probably a concentration dependence. If you don't have enough antibodies, you won't coat the parasite or all of the parasites in the bite. So we do think that there might be a concentration response relationship. That relationship is illustrated in the upper right-hand curve. Here the authors, and that's panel E, here the authors refer to that as dose-response relationship. I would think of this more as a concentration response relationship. The concentration of the antibody titer appears on the x-axis, and it's on a logarithmic scale. And we can see that as we increase antibody concentration, not a lot happens, and then we reach some critical threshold, and we get this kind of S-shape or sigmoid type relationship. And now all of a sudden we have enough antibodies in there to really interfere with the parasite's ability to invade the liver, and we start seeing some efficacy. And then the efficacy again is sort of that that is presented on the y-axis in terms of percentage of subjects that don't have an infection event. You can combine these two pieces of information, or these two plots, into sort of a time efficacy relationship, and that's in panel F. And there you can kind of see that the timing is important, right? The antibody levels start relatively high, they then drop off over time. That then gets piped through that concentration response sigmoid relationship, and you can see that the efficacy starts at a relatively high level, maybe around 75% or higher, wanes, and then those dashed lines represent what happens if we revaccinate or redose these children. Again, that's what's going to happen in this in the protocol coming up in 2018. Okay, so that's the original model that was published by Michael White. There's a series of papers available in the subfolders of the materials that you can download, that you can review those primary papers and get a sense of what's happening. I've tried to include all the supplemental material you might need to sort of get at different covariate levels. There's quite a bit of rich information there and very useful to, for example, if you wanted to simulate in a HIV-infected population, what would that do in terms of antibody titer, right? So as Steve alluded to, I think this is an area where pharmacometricians can bring to bear the very effective techniques that we've developed in traditional drug development. Briefly, in traditional drug development, we think about a dose-exposure-response relationship. A dose of a drug leads to some exposure level. Presumably that exposure level is relatively high after the first dosing and then falls over time. And we also think that that exposure then relates somehow to response. That response could be benefits, so it could be efficacy, protection, that sort of business. It could also relate to undesirable side effects, right? Safety events, that sort of business. So that's how we think about traditional drug development, dose, exposure, response. I argue that we can use parallel concepts for vaccines, right? A dose of vaccine leads to some kind of immunomodulation. In this case, we measure that immunomodulation by antibody formation. We could also look at T cells and B cells, perhaps plasmablasts that remember the immunogen. Right? And some very complex immunobiology that can be done to really get at what happens after vaccination. In any case, in this particular application, we measure the immunomodulation by looking at the antibody levels. And then we think that that antibody level then relates somehow to protection, right? So I hope I've been able to frame the parallels between traditional drug development and vaccine development. And again, this is an area where I think we as pharmacometricians haven't done a very good job in penetrating the vaccine development space, right? We don't apply these same concepts in terms of dose selection, in terms of schedule selection, that sort of business, right? And we normally do that as part of traditional drug development. So areas for improvement. For this audience, and for this audience only, I'm going to show some mathematics, right? Again, we have technical experts on this call. They're not afraid of a little math. We have applied mathematicians, epidemiologists, clinical pharmacologists. I think this is an appropriate thing to do for this presentation. I would not show this to my public health experts and perhaps my MD colleagues. I don't think that's going to get you invited to all the best cocktail parties. The relationship that was put together by Michael White and others for the CSP, so that's the antibody. So the antibody concentration over time, CSP of T, is a biphasic function, right? There's a peak value, that's CSP peak, and then that is there's two decaying exponentials. This is a very familiar relationship. We see this all the time in traditional drug development. When we give an intravenous drug, we often see a very rapid distribution going into tissues and then a very slower distribution. So we define the pharmacokinetics often of drugs using this exact equation, right? In this case, we've got some very different biology going on, but the parallels are clear, right? We have this relatively high initial antibody concentration, It drops relatively quickly. In fact, you can see that we're getting down to, we start maybe 1,000, get down to about 100 after 11 months. And so that's a 1 log reduction. We lose 90% of the antibody titer in a little bit less than a year. And then we carry on to this relatively long tail for the antibodies. Okay, so a very simple relationship for antibody titer. How antibody titer relates to protection is given by this formula V of T. So that's vaccine efficacy. That is described as a sigmoid relationship. This is kind of a funny presentation of a sigmoid model, but it works. Other groups, other disciplines refer to this kind of model as either a logistic relationship or perhaps a 4-parameter logistic curve. We call these Emax models, or Emax with a hill slope coefficient. This model goes by many names, but essentially it's a saturable function. You start off with relatively little activity until you reach a critical threshold. In that case, this critical threshold is beta. At that point, you start getting, seeing some response as you increase the CSP of T. That's again the antibody titer. You then get to some saturation level, and that's expressed by Vmax in this model. The rate of that change, that switch-like behavior, is given by the parameter alpha. Okay, this is a nonlinear function. When a modeler or other groups or a mathematician tells you you've got a nonlinear function, that means that your intuition may not be good. That's what we're saying essentially, that we can have behavior that is unexpected and dramatic at a change point in the model. Right? So when you have a nonlinear system, that really calls for simulation tools to explore it, because our intuition may be poor here. Okay, that's what nonlinear means. So I showed you the model for vaccine protection and antibody titer. There's lots of parameters in that model, 7. So then the question becomes, what product qualities, in this case the inputs to the model, the parameters of the model, should we focus on to improve, again, a hypothetical follow-on malaria CSP vaccine, starting from RTSS as the base case? I showed you that titer function. It's a linear biphasic function with at least 4 inputs. The peak titer value, which is the titer after the last dose. The rho parameter, which describes how much of that peak disappears quickly versus slowly. And that's a fraction. And then either a half-life or a mean residence time or elimination rate, however you want to characterize that. For that short-term titer disappearance and that long-term titer disappearance. Okay, so 4 parameters, linear model, but clearly there's lots of different behavior we could get out of the model by changing these 4 parameters. Protection is nonlinear. Again, it's an Emax type model with at least 4 inputs. That previous function, right, the CSP antibody over time, and then the parameter potency, beta. For pharmacometricians, we might think of that as an EC50, an effective concentration that provides 50% of the maximal output. A shape parameter, alpha, that kind of describes how steep that protection titer relationship is. And then finally, Vmax, which is the maximum protection if you provided infinite titer. Of course, nobody ever gets infinite titer, but that tells you the saturation point of that signaling curve. Okay, so 7 parameters, nonlinear model. Which of these should we adjust? Which of these is going to have a meaningful impact on the vaccine efficacy? Right? What are we going to do here? Not all of these will yield similar results. So to answer that question, we're going to use the model in simulation mode, the forward problem. We're going to implement the RTSS titer protection model and use it in simulation mode to answer these what-if questions. Again, I will remind you, generally nonlinear systems are not really intuitive. To follow this analysis, you should install R. That's an open source statistical platform language. You can download it here. Many other disciplines use this tool, so I hope I'm using a pretty, in theory, you could do this in MATLAB too if you're a MATLAB fan. Inside of that zip file, you'll find a file called rumme.r, which tells you what you should do with it. That will install a bunch of other extensions in R that will help you then run these examples. Okay, and I'm going to assume that as we move through this, that we've looked at that, or at least have a passing understanding of that, the R language, and have sort of maybe installed the R code and looked at that. So let's look at an example, right? So an obvious thing to do would be to increase the antibody potency. The other obvious thing to do would be to increase that antibody's long-lived half-life, right? That would give us, the potency increase would mean that at lower concentrations of antibodies, we provide more protection, so that's good. The other thing we could do is try to extend that tail of protection, right? Make the antibodies hang around for longer over time, and those two things should then provide greater protection in these 5 to 17-month-old children. So some options. You can take a look at this in the simulations.r code on lines 20 through 35. And I think I actually have that open here. Yeah. So kind of just get a sense of, I'll pause briefly in the presentation and kind of show you some code, right? These are all the different packages that we're going to install to kind of get this done. And then there's a bunch of R code here. And I've tried to do a reasonable job of documenting what's going on. But these are the titer and protection functions that are in the model, right? Just some pretty simple algebraic relationships. And then we're kind of going through a bunch of different simulation cases. What if I take the potency of the drug and increase it by, leave it the same, increase it by a factor of 2, increase it by a factor of 10? What would that do? Presumably, if you increase the potency by a factor of 10, that's going to lead to much better protection. The other thing that I could do would be to change that second phase half-life. So I do that same kind of trick here again, right? Increase the half-life, leave it the same, increase it by 2, increase it by 10. Increasing things by a factor of 10 is kind of challenging to do. It's possible, but that could be kind of tough. So and so you can sort of take a look at those simulations, and you'll be able to run the code and reproduce exactly what I'm showing you here on the PowerPoint. So if I do that, what happens? Well, on the left curve here, I'm showing you some projections of antibody titer. And again, that's expressed as in terms of units of EU per mil, which is concentration. The x-axis is time, units of years. And for the titer, modifying the potency doesn't adjust the titer value, the antibody concentration. But changing the beta half-life, that second phase half-life, that really does change the curves. And you can see that in that left panel there, right? As I start from 1.64 years, that's the lower curve here, go up to 3.29 years, and then go up to 16.4 years. At 16 years, we get really a flat profile, right? But again, it doesn't change the potency at all. What you can see that if we keep lowering the potency, so imagine this case where we've made the potency down to 10 EUs per mil and can have this 16-year half-life, we're way above the effective antibody concentration. This is going to provide lots and lots of protection to these subjects. When we look at the protection curve over here on the right, this is again efficacy against CSP infection. Well, now I've got 3 different beta half-lives, 3 different potencies. I end up with 9 cases, right? And this lends itself to what I would call kind of a pile of spaghetti. It's just a bunch of curves. And maybe I, as the author here, can dissect what's going on, but really nobody else in the audience can figure out what's going on here. So this is an example where when we start running these simulation cases, we have to think carefully about how do we present this information to non-specialists and other audiences. And I would put this presentation on the right here as a terrible idea. This is not what you want to do, okay? Preferentially, what you'd like to do is maybe take one of those simulation perturbations and split that out in terms of facets, right? So on the left, what I've done is I've taken all of the half-life cases, which is the base case, 1.64 years, and put them in a single panel. And then in the middle case, where I've doubled the half-life, that's 3.29 years. And in the right panel, where I've increased it to 16.4 years. Right, so now this is a bit more digestible. You also notice that I've dropped the antibody titer. I don't display that here. I'm only displaying the efficacy against infection, because that's what people care about, right? Yes, knowing what the antibody titer level is important to define protection, but we care about the antibody concentration exactly in the same way we care about the pharmacokinetics of a drug, right? It's not, the pharmacokinetics aren't interesting as what does that do in terms of efficacy and safety, right? So I'm intentionally dropping that display because it doesn't really help us understand what to do or how to take a decision. So I would say that these plots are okay. You know, you can kind of see that as I increase the potency from its standard of almost 100 EUs per mil in the black line, as I increase the potency, make it 50 or make it 10, I start seeing more and more protection, right? And so we start getting into a case, especially in this upper right panel, where yeah, we've kept the protection well above 75% in this population, but is increasing the half-life by a factor of 10 and the potency by a factor of 10, is that realistic? Can we do that? It's not at all clear to me that a factor of 10 change is easily doable. I have a great deal of respect for our drug developers over at GSK, and if they could have made something, you know, with a factor of 10 better, they certainly would have, right? I think this is a moderately more successful display of the information than we saw in the previous slide. I've kind of sort of trimmed out some of the sort of spaghetti-like behavior. I would say it's moderately successful. I would prefer a plot like on the right here. And what I've done is instead faceted by potency, right? So this base case of 99.2, that shows all of the protection curves. And then when I improve the potency by a factor of 2, that's in orange. When I've improved the potency by a factor of 10, that's in blue. And the reason why I would prefer this is many of these curves, at least in the initial phase of decline, which I didn't change at all in the model, those curves are superimposed. And the way that human perception works is because those curves are superimposed, your eye is going to pass right over it, right? So you're focusing the audience's eye on the bits of the plot that we really care about, right? All these curves are superimposed. You're just going to kind of pass that by, and then notice that it may be year 1, 2, 3, 4. That's where we start seeing a meaningful difference in the changes in the model parameters. So I think this is a much more successful display of the data, and this is something you probably could take to, you know, your MD colleagues and other non-specialists in public health, right? They would be able to digest this amount of information. So I think a relatively more successful plot. So again, one of the challenges in pharmacometrics is to show the right amount of information. So I've just shown you 9 possible cases. If I tried 3 cases for the 7 model parameters, I'm going to get more than 2,000 cases to display. And that's going to be really, really difficult for anyone to understand. Some of the assignments, the sort of the take-home work, walks you through running those 2,000 cases and then trying to figure out how do I extract the key information from those simulations. And that's a very difficult thing to do. So there's some good examples there in those sort of take-home work. Here, I'm going to try to show you an example of how you might do that most effectively. What I've done, again, I'm just focusing on protection. I'm not looking at antibody titer at all. I start with the base case, which is the RTSS vaccine as it stands. And I've intentionally used the base case as a black line, because the most common plot that we look at is black lines on a white background, right? So something about using that default color aids the mind in understanding that's the base case, right? That's the default. And then as I increase the potency, I go from black to orange and then up to blue. Blue is a factor of 10 change in potency. So maybe blue is blue sky thinking, right? That's probably not difficult. That's probably quite difficult to do. So I'm using these sort of tricks of human perception to try to get my point across, and with the least amount of effort on the part of my audience. I do one fancy thing here where I look at a 2x change in potency in orange and a 2x change in half-life, again in orange, but now I go with the dashed line. So you know these two lines are related because of their choice of color, and you know that that dashed line intuitively is not like the others. I've done something else which is not like the other cases, right? So here, the point I'm making with this slide is, this is, with the black line, this is the efficacy of RTSS right now. And you can see that after a year or so, and a year and a half, I've dropped below 50% efficacy. Not surprisingly, in the protocol that's going to be introduced at the end of the year, we're going to revaccinate at 1.5 years. Why is that? Because the efficacy has dropped down, right? The other thing that this graphic tries to convey is, yes, if you made a factor of 10 change in potency, that's the blue line. And yeah, you can indeed keep the efficacy to be much, much higher. Alternately, rather than making a single 10x change, which might be very difficult to achieve, you can make two 2x changes, right? And because of the model and that nonlinear behavior, I can get a pretty good response out of just a couple of modest changes. That's the orange with dashed lines, which keeps my efficacy above 50% for out to 4 years. And in fact, you can see that those curves, yeah, the blue line is starting higher, but the slope of that blue line is, at some point, they're going to meet, and that orange case is actually better. Right? So this is the kind of plot you would like to present to people that are thinking about generating another vaccine, to put the idea in their head, rather than trying for one transformative improvement. Perhaps you would be better off by looking for some modest changes that generate synergy. Okay? So in summary, you can, if you shift the potency by 10x, that does provide protection against malaria, but greater than 50% at 5 years. So that's great. However, the point I'm trying to make with these particular plots, and again, there's lots of other things that can be done with this model, is that a couple of modest changes can shift the protection to around 50% at 5 years, right? So rather than, trying to make this very, very big lift to get a 10x improvement, a couple of modest improvements might be the way to go. And I should comment, this is a live question within some of the clients that I work with. What can we do here to improve this vaccine component? So there are other product attributes that can be modestly adjusted to get improvements in potency. That, in a clinical pharmacology sense, that's called synergy. I wouldn't use the word synergy because it means something else in lay terms, although here in this case the two concepts are highly related. You can also use the model to look at other potentially correlated product attributes. You may find that if you modify positively one facet of the product attributes, you may negatively affect the other aspects, right? Perhaps by increasing that second phase half-life, you generate a lower initial titer, right? That's just a consequence of how the immune system processes that imaging after you make that change. So how do you adjudicate where you've made an improvement in one area and a hit to your product attributes in another? Well, that's a great use for this model to work through those kind of what-if questions where you can use the model to evaluate trade-offs. And that's a really useful tool to provide for people, and especially in the public health arena, right? The other thing that this model points out, which I haven't really spent any time talking about, was given a goal of trying to provide a 2 to 5 year protection window, proof of concept study durations should be really carefully considered, right? I showed you that biphasic decay, so that the efficacy is quite different in the first year than it is in the subsequent years. And you would be potentially quite misled to only look at short-term studies because you would get that early initial efficacy and be quite misled about what will happen over time. This is very important because we're beginning to develop controlled human challenge models where we actually infect volunteers with malaria and then provide an immediate intervention of some kind. Well, is that the efficacy that you see in those very short duration studies of 20 days, is that in any way relevant as to what might happen at 3 or 4 years down the line? Even a 1 or 2 year study could be misleading, right? So I'm cognizant of that because the study that's going to be kicked off is, dosing from 2018 to 2020 and then some follow-ons. So we're going to capture several years of efficacy. There's that redosing that happens at 18 months. I'd be a little bit careful about over-interpreting what that might mean if you then deploy this over time. The simulation tool that produced these plots are available in 2 places. One, you can click on this link and that you can then run it through a web browser. I've also provided the RShiny application in the zip file that you can download. And you can then run that web-enabled simulation tool right on your desktop. Right? It's a pretty neat. Let's see if I can pull up well, I can't easily pull that up now, so why don't I leave that at that? The version that you have in that zip file actually has extensions to this tool that are not available in that online version. So you actually have a better version of that simulation tool available to you. And of course, Colin, Steve, and I are very serious about increasing capacity and providing feedback and help to people that are interested in beefing up their pharmacometric skills. So by all means, send me an email. I'm happy to help. I did get a question by email from William Matembo. And I could certainly answer those questions now, but maybe I can turn that back over to Colin. I'm thinking there's probably some questions through the chat, and perhaps we can start with those.
So Mike, maybe you sit here for a minute. What I would like you to do is what you were trying to do just now, to take participants through that directory structure and what the files are.
Yeah, okay, good idea.
Let's do it so that it stays on the recording.
Yeah.
And hopefully we don't break the system. It's all working so well already. And in the meantime, Steve, I wonder whether you could get ready to answer Elifert's question that came through a little bit earlier.
Yeah,
Okay.
Colin. So that was a question that Elifert had asked about combining vaccines with therapeutics that are going to provide some level of anti-gametocytes like primaquine, and the latest ones in that category, that are coming forward in some of the new antimalarials. So, to my knowledge, they're not combining the two in the upcoming trial. They do test people to make sure that they're clear of an ongoing infection, and I think they just use standard standard malaria therapy drugs, ACTs at that time, for clearing parasites in any positive patient before vaccination. So I don't know that they are planning to do that. And the challenge I think you run into is that the duration of the anti-gametocyte properties of most of the current therapeutics is not nearly as long as the duration of coverage and duration effect that you're getting with the vaccine. So you still would be ending up potentially short as a consequence. But you could at least have a good chance of eliminating or reducing the potential for transmission in a particular region if you did do those two together. I think those are some of the simulations that, in the earlier work that I showed with the epidemiological modeling groups, as they start to combine interventions, those become some of the things that would be interesting to think about and explore to be able to assess and forecast what we think might be the impact of combining some of these interventions, and then validate those forecasts in a prospective study.
Thanks, Steve, and back to you, Mike.
Sure. Okay, so this is the zip file structure once it's unpacked. And I'm hoping the only thing that's not terribly self-explanatory is this cryptic www folder. And that's an artifact of our Shiny that if you want to publish PDFs and that sort of business, you have to put it in a folder called www. So I apologize there, but that's just sort of a technological limitation. Inside that that www folder are all the primary references. So principally, that's the original paper that came out in 2014 that walked through the phase 2 analysis, and that was sort of in adults and a couple of other populations. There, they were looking at different schedules. So do we vaccinate twice separated by a month? Do we vaccinate 3 times separated by a month? And then what happens in, say, HIV-infected populations? What happens by different age groups? Do we see any reduction in antibody formation when we have concomitant vaccinations? Right, many of these vaccines are given, especially for children, kind of together in a series. And what happens? Do you get a reduction of immunogenicity when you give multiple vaccines, right? So that's the 2014 papers. In 2015, that's the sort of the analysis of the phase 3 studies in children. So that's where we're really drawing most of the model parameters from to make simulations for the 5 to 17-month-old children. There is a paper, I call your attention to this one. If you just want to read one paper, that's the White 2015 Mathematical Models for Malaria Control. That's sort of a non-specialist paper where the Imperial College group is talking about what role does modeling simulation have in sort of predicting malaria control, and they use it very lightly and with kind of a light touch. They use these models to sort of do some simulations, and I think if you had to pick one paper, it's not quite a review article, but it really does kind of set the stage, and I hope would kind of get the salivary glands going around what could we do, what should we be doing with models in this space, right? So that's the www folder. The presentation itself is available there as a PowerPoint file. There's this very friendly-looking, shouting file called runme.r. And it really just needs to be run to actually help you install packages, right? I'm using a variety of extensions to R to facilitate working through the simulations. I personally use a lot of tools from Hadley Wickham's Tidyverse. Hadley Wickham is a statistician, now has gone to work for RStudio, and this series of packages uses the concepts of pipes like you would use in an operating system, Unix type of environments, or even SAS for that matter, of sort of piping data frames or tables of data through a series of processes. So I think an extremely useful set of packages. ggplot and ggthemes are used to actually produce the graphics. I do use the logit function from the gtools package, and then these are the tools you need to make Shiny applications. So I think, I hope, fingers crossed, if you ran this, you would then get all of the packages installed. Things can be a little tricky with if you're using RStudio, but if you're using command line R, I think this would all run very smoothly. If you run this, what will happen is it will install a bunch of packages and then load the RShiny app. So it'll pop up a web browser and you'll be able to run the application from your desktop. When you exit that, then it will run this simulations.r code, which reproduces all the plots that we saw in the presentation, right? So these are these protection plots, and we'll actually write those out. And simulations.r is this. We looked at that previously. That really is just running through all the different simulations. And again, it's not a lot of code. It's maybe 100 lines or something like that. So it's quite efficient and should be pretty digestible. And you can use this as a jumping off point. Probably also worth pointing out problems 1, 2, and 3, where I start walking through, like, how do I run a single simulation? Let's start there. If I don't know anything about how to use simulations in R, This is 20 lines of code that runs a very simple univariate simulation. And then as you start stepping through more complex problems, problem 3 says, well, run several thousand simulations and try to figure out which of these parameters in a sensitivity sense actually drives very good protection, right? What parameters uniformly need to be in a particular way to generate very good protection, and that's a sensitivity analysis that really helps you focus your effort. Not all parameters in a model, the outcome is not always sensitive to every model parameter. So this helps us cut through. We've got 7 model parameters. They're not all equally important. Which ones should we be focusing on to improve efficacy in a follow-on type of vaccine, right? So a little bit more complicated. And I would say I didn't come up with a particularly great solution for how to visualize several thousand outcomes. I very much suspect that there are audience members on the line, especially my epidemiology colleagues, that have a much better idea about how to use heat maps or other type of diagnostics to get at, how do we really show this information, right? So I don't present this as a fully worked problem. Again, I suspect people here on this call have a better idea of how to do this than I do. Okay.
Great, Mike. So just before, you can stay there. Just before I interrupted you, you said that you had a question that came by email. That's absolutely fantastic, folks. Please send us your questions or post them on the download site. But do you want to comment on the question?
Yeah, so this came from William Matembo, and the question I thought was excellent. There's a couple of questions, but one of them was, well, we noticed that the vaccine efficacy is better in 5 to 17 month students than 6 to 12 week. Does that trend continue as we increase in age? And if you go through some of the supplemental material for these publications, there's a table S6 that reports the results for the adult population. And I think what you see is that the 6 to 12 week subjects who have a relatively low titer level are the exception, right? The adolescents and the older kids, adolescents and adults, seem to have a relatively similar antibody response. Why is that? Well, in other vaccines, we found that vaccinating early doesn't really lead to much response. They don't have a fully developed immune system yet. And in fact, many vaccines we wait until 3 to 6 months. I think for influenza, we don't vaccinate until maybe 6 months of age, 3 months of age, for exactly this reason. We don't get a robust immune response in these infants. They're still relying on transferred antibodies from their mother while their immune system is becoming more and more competent, right? So take a look at that supplemental table S6 for details on that. The next question that William asked was, well, could we revaccinate every long-term half-life? That question in and of itself is exactly the drug development. That's drug development thinking. We very frequently dose drugs based on their half-life. If you have a very short half-life drug, you have to give it 2 to 3 times a day. If you can generate a long-lived half-life, for example, Aleve versus ibuprofen, you can then dose once a day or maybe twice a day, right? So likewise for vaccines, yes, one solution to RCSS's AS01's lack of efficacy after 2 years or 1.5 years is revaccinate. So yeah, a great question, and that's absolutely appropriate thinking. The question I would have, though, is that okay from a public health perspective? The cost. Can we routinely access these children to get them a vaccine every 2 years? What is the public health cost associated with doing that? Is that realistic, right? And I think that's something that is going to have to be wrestled with at a sort of national and a county level and in different areas. I guess it depends on your healthcare budget, right? What can you afford to do? And then the other question that William asked was, well, do I need to return any homework to you? And the answer there is no. I'm happy to take some emails and help you answer some questions, but I'm happy to do that. But this isn't sort of a class in a classical sense. But my commitment, and I think Steve and Colin feel similarly, that if students that are interested in this reach out, or faculty that reach out and are interested, we'll absolutely lend a hand here. Again, this is a capacity building as part of this mission for this group. And I think actually Colin and Aida will have something more to say about mission statement in a minute. Okay, so great question, thank you.
So fantastic, thanks Mike. There have been some questions that have been coming through on the chat line. Unfortunately, I'm using a separate login, and from time to time I've dropped off, but all of the questions are saved and are being recorded. So we have one more presentation that will be Aida from Uppsala. But Professor Ogutu, you had something to say. I don't know whether you want to do it now or whether you'd like to do it after Aida's presentation. Okay, fantastic. So in the meantime, please continue to post your questions onto the chat line. They will be recorded and we will go through, moderate that, and come back to you with answers. With that, let me now introduce Aida. Aida Kawuma, who's going to do the next presentation. And actually, Mike's last few comments about whether this is a classroom or not, is a nice segue into Aida's presentation. So Aida is going to talk to you about what the plans are for the next stage. So Sinead, if you could then mute the room here at Strathmore and open up the room in Uppsala.
So good morning, good afternoon, and indeed good night for some of you. I know some of you are calling in from various parts of the world where it's getting late now. So as Colin said, my name is Aida Kawuma. I'm a scientist from Uganda, pharmacometrics scientist, and I'm currently a doctoral student at the University of Cape Town. And it's my pleasure today to introduce to you a new initiative called Pharmacometrics Africa. So Pharmacometrics Africa is, as I was saying, a non-for-profit legal entity that has been set up in South Africa. And it's going to run under the stewardship of Gary Martins, Colin Pillai, and Paolo Denti, which with support from the Bill and Melinda Gates Foundation. So Gary Martins and Paolo Denti are based at the University of Cape Town, and Colin Pillai is an advisor to the Gates Foundation, as he introduced himself. So today is our inaugural launch, and I'm glad many of you managed to join us and tune in. And so I'll take you through what we hope to do, what our mission is as we walk this 3-year journey. So the thinking behind the initiative was that the low and middle income countries, especially Africa, have a very few number of trained pharmacometric scientists. And because of that, you realize that we have a large unrealized potential in these areas. And so the initiative really hopes to remedy that situation. And it's going to initially focus on Africa as its main area. And it hopes to do this by providing trainings via distance learning and hands-on workshops, with the aim that all resources will be open source, and also hopes to foster country-level networks for pharmacometric scientists and support the different university groups present on the continent to try and help them into being centers of excellence. And the end result really is that we'll increase the number, the quality, and quantity of highly trained pharmacometric scientists on the continent. And so I would like to encourage you to read this paper by Colin Pillai and colleagues, which really states and makes a strong argument for why it's beneficial to encourage and foster this discipline on the African continent. We feel that with this initiative will at least start to increase the number of scientists and hopefully go a long way in improving patient care on the continent as well. So there have been a few previous trainings on the African continent. That was the very first training in Cape Town. There've been others in Uganda. You can see me right there stuck in the middle. I've benefited from some of these initiatives, and they launched me into this career. These trainings have experienced a lot of support from pharma companies and from various universities and very dedicated individuals from the United States and from Europe. As some of you may be able to recognize yourselves, I see you calling there. And lastly, that's the most recent training that was held in Cape Town in 2016. So there's been a number, but we hope to boost more of these. So what's our vision? What's our mission? Really, what we want to encourage is that we have more locally relevant best model analysis to improve patient outcomes on the African continent. So what we'd like to see is that, one, we increase the number of qualified quantitative scientists, but who should be working on locally generated data, and then engage in international research collaborations to improve how existing and new drugs are being used for previously underserved African populations. So we do realize that in this field, many drugs that are used on the African populations are not optimized for these populations. So our aim really is that we hope to see a world in which data that's generated on the continent is analyzed by locally based pharmacometric scientists, and then they engage with international research scientists, so that really we improve the participation of African scientists. So like I said earlier, we're going to strengthen centers that are previously already doing some of this work, such as Makerere University, some in South Africa, so that we form centers of excellence that can foster research collaborations. And we also hope to host collaborative events in which we'll have international experts join us and hopefully showcase African talent and science as well. Eventually, we hope to increase the level of sophistication of the pharmacometric contributions to clinical science in Africa. On the continent right now, there's not a big appreciation of what pharmacometric methodology can do. There seems to be a gap, like Michael talked about, communication. Many of our colleagues in public health are not aware just how powerful this tool can be and how we can use it. And we've also, I think, done a poor job at showing them how good this tool can be. So really our vision and mission is to remedy that. So how will we do this? So we hope to offer trainings for a wide range of interests, from those who are keenly intrigued or interested to those who actually want to take up a full-blown career in this area. So we will hope to have webinars every 6 to 8 weeks, such as this, which has just been done by Stephen and Michael. And so they'll ideally be 1 to 2 hours long, and these will address topics of global relevance, and all materials will be open access. We will then also offer online training courses, typically 10 to 12-week university level courses. These will be offered by tutors and faculty who are subject matter experts. These online courses have already been tried out and done on the African continent. I did one such training. And these trainings ideally drain scientists from all over the continent, from different parts and places. And then ideally, after having an online course, we would then invite scientists for face-to-face workshops, typically 3 to 5 days, where we get hands-on sessions and get to liaise and interact with the actual tutors. This will be organized at least annually in a different country, and this is to maximize attendance of local scientists. And these trainings, both the online and face-to-face, would have a competitive selection process. So for you to get in, you'd have to, show some level of interest and some level of commitment, and there would be some sort of competitive selection involved. So at this juncture, I would like to say that if any of you have topics that you think are of interest globally or are keen to undertake, please let us know such that we can prepare a webinar for that particular topic, or make sure that we incorporate it into online or face-to-face. So all our activities will culminate in the WCOP 2020. I'm pleased to announce, as some of you might know, that the World Conference on Pharmacometrics in 2020 will be held in South Africa, in Cape Town, and so we are looking. So we hope to culminate all our activities with that workshop. So this is a workshop that's held every 4 years, and WCOP was created to augment PAGE and ACOP, which are the premier European and American modeling meetings. WCOP 2020 will bring together a wide array of scientists and academics, clinicians from various disciplines. So it will be an opportunity to meet, discuss, make contact, explore opportunities. So this is going to be hosted in Cape Town, like I said, by us, this initiative, Pharmacometrics Africa, in conjunction with the University of Cape Town, the Division of Clinical Pharmacology. So this seems a while away, but trust me, it's only 20 months, so 20 months from now. So I encourage you to go to your diaries and book it off in your calendars. You must, it's a must attend. And I also encourage you to visit the website where you will learn more about WCOP 2020. And lastly, I encourage you to please keep in touch and register your interest. Right now, you can visit the website, the link over there, and you'll be directed to Pharmacometrics Africa. In the pipeline, we are setting up a dedicated Pharmacometrics Africa website. This will launch soon, and we'll all let you know when that is up and running. This will have course announcements and registration details. It will be a site also where you can download training material as well as progress updates. So please feel free to reach out to any of us. Our emails are there, and to any of the others you've listened to today. So thank you again for coming for our inaugural webinar. Just in addition to that, later on this year, the OA University, in conjunction with the University of Liverpool, will host a PBPK meeting in Nigeria. This will be coordinated by Dr. Adeniyi in Nigeria. So please feel free to reach out and register your interest for that. So thank you again for listening and for tuning in.
Sinead, thank you very much. Aida, thank you very much. That was awesome. In the process of doing your presentation, you also answered a question that came through the group chat from Eddie, who is one of our African brothers from Tanzania that is currently doing a postdoc out in the US. And he wanted us to give some indication as to how we would motivate the African pharmacometricians. So we are very nicely within time. We have half an hour of normal time left. We are hoping that we can actually close earlier. Professor Ugutu is in the room right now, would like to ask or make one or two comments. In the meantime, I can see some really, really interesting questions coming through. There's one that goes to the heart of modeling from Wigilia. My apologies if I haven't said your name correctly. Mike, do you want to make a quick comment on that, and then we can follow up with a more detailed answer afterwards?
So the question that we've got really is, what do we do around children with increased risk? What do we do around vaccination for pregnant women? What do we do with sickle cell or diseased children? That generally speaking, in pharmacometrics, we call that covariate analysis. We're always looking for where does the efficacy or safety change and in what subpopulations, and does it change enough that we need to do something about it, right? So if you ever read any of the labels of any medications you get, there's some discussion around special populations, and there's some discussion around, well, when does this drug need to be modified in the case of, say, renal insufficiency? That's exactly the same question that's being asked here around what do we do around, do we need to do anything different in more susceptible and vulnerable populations? I can comment a little bit on the, what do we do about pregnant women, right? They're potentially at higher risk? What do we need to do in that particular case? There has been a movement around vaccination of pregnant women. And we do that because, well, for exactly the reasons that we noted, that RTSS has lower efficacy and lower titer in younger children. Often you can't vaccinate these younger children because they don't have a complete immune system. What we can do is we can vaccinate mom. She generates antibodies. Those antibodies are transferred via the placenta, so the child is then born with some antibody protection from that maternal source. So we've done a little bit of modeling work there on influenza, and we've looked at the Tdap, or the tetanus, diphtheria, acellular pertussis vaccine. And one of the things we notice is there may be a right and optimal time to vaccinate mother. We know that it takes some time for the antibodies to develop in mom. Then we also know, and I showed you those graphs at RTSS, that the antibodies then wane over time. That suggests that there's an optimal moment to vaccinate mom, right? And so the timing of that, and how do we select that population? I don't think we're at the point of understanding that, but that is exactly the type of analysis that pharmacometricians do in a classical drug development context. And we should be doing that also with vaccines. Okay, so great question. Sorry I couldn't provide a more thorough answer, but great question.
Right, thank you very much for this, and I think possibly it's fairly an interesting area, and looking at possibly the relationship between effect and drug dose is more or less linear, as opposed to what we might see in vaccines, where there are several things in underplay that possibly influence the outcome in terms of protection against the disease. And I think this is what is going to be very critical, especially dealing with malaria, where the understanding of the immunology is fairly not as robust as it should be. And when we look at it, we don't know why it wanes off. And then you might also not understand when possibly the dose effect, where you reach the point of energy, where you either overwhelm the body with the doses of the antigen that you give, and then you get no response. And possibly whether this has anything to do with what we might look at the fractionated dose that is going to be tried, and see whether that gives you a better outcome, and whether the booster dose does much of the work and possibly prevent this. And there's need for playing around with this and seeing what are the other variables that possibly come in terms of exposure to other vaccines and other things that possibly happen to children. And I think this makes this a fairly welcome area to start doing a bit of work, especially with the pharmacometrics, which then see how this can be applied into vaccine development, or just optimizing the doses or the timing of the administration of the vaccines to make sure that we fully get the benefit of what we need out of it. And I think that's one of the things that possibly we look forward to as we look at what Mike is going to work on, and possibly see how this happens, especially with the new vaccines that possibly will be developed, and see how you can start playing around with these, the earlier developmental studies that we are during the challenge studies, or during the phase 1, where you're just basically looking at the antibody kinetics and look at some of these things and see how this plays and how it can determine what to work with or what to discard at early developmental stages. And I think these are going to be quite key questions, how to factor the whole pharmacometrics into the whole vaccine development process. And also just looking at possibly on the Pharmacometrics Africa, it might be nice to possibly have a few studies targeting a few diseases and a few drugs that we know definitely are going to have a dose optimization or modification, especially dealing with different population, or malnourished children, or just the possibly children within the African region, because we know sometimes looking at some drugs, we know there's quite a big variation. Like dealing with a common drug that we generally use, if you're using phenobarbital in Asia, the dose is 5 milligrams per kilogram body weight for children. If you're using in Africa, the dose is 15 milligrams per kilogram body weight for children, especially if you're doing active treatment. And I think there's some of the things like what we found that in African children, even chloramphenicol requires a loading dose, which was not part of the whole way that the drug is dosed in the rest of the world. And I think currently it is being used that way, but we realize we need to do this. I think we might need to look at a few products that possibly we can apply this and start seeing how we can then get the bigger outfit into the public health sector so that people start buying it into the whole remit when they see the real benefits and real treatment paradigm shift that are going to come out of it. I know that is more costly, but we might look at just doing a few PK studies for a few drugs that are possibly specifically this area that we think there's likely to be a bit of shift in terms of the way we optimize the doses of some of these drugs. And also that can help us sell the whole drive. And I think pharmacometrics alone might find itself finding it, to find a constituent might be difficult, but if we link it to much more PK work and clinical trials, then we are likely to make much more inroads and get much more buy-in much faster and build the community, because then people can see the real utility, which might be clear to us, but not very clear to the general audience within the scientific community.
I think that those were fantastic contextual statements from Professor Ogutu, also telling us about existing drugs and new drugs that would come up that would lend itself to these types of analyses. So what I'm going to do right now is to just make a few concluding remarks to close this meeting. Again, I see some very interesting questions coming through the chat line. So firstly, if I could ask Sinead to keep the group chat open for the full duration of this meeting, even though we might close earlier, so that people could record their questions rather than go to the website. Sinead, what I'm also going to do right now is to share and remind people about the place where they could, hoping this is it. If you go to the link shown up on the screen right now, the learn.faculty.ie link, what you could now do is go to the forum at the end of this meeting and log in any questions that have come up. Of course, you can continue to put your questions up until the end of this meeting on the Zoom chat line, but thereafter log it on this website in the discussion forum. This forum will be moderated, and we will post some answers to your questions. In addition, we will post a survey on this website, and Sinead, you could just come in and let me know if there's an alternate place where you will post the survey. In the survey, colleagues, you'll have the opportunity to give us some feedback as to how this webinar went, as well as give us some indication as to what you would like to hear about in the future. Sinead, anything else on the meeting logistics here?
Colin, you've summed everything up to a T. So just to encourage everybody to please log in to learn.faculty.ie as a guest, and then go to the material for the webinar. Everything is there and downloadable. We'll have the recording of this meeting up there tomorrow, and everything's in one place. So we look forward to your feedback, and thanks everybody for joining today.
I want to really thank the faculty, and Steve, you're a trooper. It's close to midnight out there in Seattle. Thank you so much for staying up late and for participating. Mike was here in Kenya coincidentally for some very nice social activities that he's involved with to benefit the communities here. Mike, thank you for suggesting to come and do this, and for doing such an amazing presentation, beautifully paced. I was monitoring feedback on the chat line. very nicely paced, beautifully organized. Thank you so much, Mike. You've actually set a very high bar for the future webinars. Aida, thank you so much for doing this from Uppsala and for the group that you have accumulated there. And please convey our thanks also to Mats Carlson and the group there for having provided the opportunity for you guys to bunk lectures in order to come and attend this session. So in addition, here out in Strathmore, Professor Ogutu, Beth, Florence, Mercury, Brian, the logistics have been just absolutely fantastic. And we deliberately wanted to do this initial launch from within an African setting. And I think it's clear. Let's wait until we get the feedback. But for me, it's clear that this can work, and this recipe and this method can work. Sinead and Jeremy, again, from my side and from everybody around here, thank you to Faculty Capacity Development for having hosted this meeting. As we go through, we hope to be able to work much more closely together on this. Last but not least, I think just doing this session on the RTSS vaccine for a disease that's so important within this part of the world was, you might think that this was carefully, strategically planned, but thanks to Mike, it fell in our laps. The vaccine itself is not perfect, that's clear. You heard that from Steve at the beginning, and if you've looked at the data, you will see this. But of course, there's a pipeline of vaccines, and this is the only vaccine that's registered right now. And hopefully, as we go through the pipeline that's there in phase 1, phase 2, this is going to get better. And then what we showed today was the power of mathematical modeling and computer simulation. And this power extends all the way from discovery through to use in the field. So again, if you're monitoring the write-ups around RTSS, you would see that people are talking about, do we know what the cost effectiveness or what the public health benefit with this? And with all of these activities, model-based methods or mathematical methods can provide the quantitative input to be able to help the decision makers to make their decisions. So we're really thrilled that we were able to launch this particular activity with this example. And with that, let me, for one last time, remind you to please post your questions, post your comments, post your feedback. You've got multiple ways in which you could do this, either through the individuals that gave you the information about this particular webinar, or through the email addresses that you've seen on various presentations. So with that, thank you very much, and I'd like to close this meeting. Thanks, Sinead. You can stop the meeting, but keep the Zoom chat line open so people can continue to post comments.